Hey everyone, and welcome to this explainer. As a lead engineer, I literally spend my days staring at incredibly complex machinery, trying to figure out exactly why things shake, rattle, and roll when they definitely aren't supposed to. It's like a giant puzzle. Today, we are going to bridge that crucial gap between the physical reality of a shaking machine on the factory floor and the mathematical models we actually use to troubleshoot it. Let's dive in and decode how we translate physical components into mathematical equations together. So, what's on the docket for today? First, we'll cover the basics of mechanical vibration. Second, identifying the causes of vibration. Third, the four fundamental elements. Fourth, physical to mathematical models. Fifth, challenges in modeling mass. And finally, number 6, degrees of freedom explained. All right, let's jump straight into section 1, basics of mechanical vibration. Before we can fix a shaking machine, we really have to define the problem. So, what exactly is a dynamic disturbance? Well, imagine a massive earthquake hitting a skyscraper, or the intense airflow rattling your car body when you're driving at high speeds. If an external excitation were the only force acting on a system, it would just exhibit what we call simple, rigid body motion. That just means the whole object moves together as one solid piece. But in the real world, most systems are actually elastic. When a disturbance hits them, they stretch, they compress, and they respond dynamically. And that brings us to how we actually define vibration for a beginner. It's the cyclic or oscillating motion of a machine, or a machine component, from its position of rest. Essentially, it's a to and fro motion initiated by some applied disturbance, specifically when there's a restoring force trying to push it back to where it started. To talk about this stuff as engineers, we really need a common language. So let's run through a quick terminology guide. We measure how far a component moves. That's displacement, usually measured in meters. How fast it's moving is its velocity in meters per second. The rate of change of that speed, that's acceleration in meters per second squared. And perhaps most importantly, we look at the repeating cycles. We measure frequency in hertz, which means 1 full cycle per second, or sometimes we use angular velocity in radians per second. We also measure the amplitude to find the absolute maximum extent of that cycle. Okay, moving on to section 2, identifying causes of vibration. Let's shift our focus to what actually triggers these unwanted movements. Let's contrast two very different types of real-world mechanical faults. First, think about an internal flaw, like a bent rotating shaft. This causes an inherent repeating force right inside the machine. Now, contrast that with an external installation failure, like loose motor bolts. Improper mounts or completely missing isolators can turn a perfectly good, healthy motor into a severe vibration hazard, simply because the heavy machinery just isn't restrained correctly. In industrial environments, we use a pretty extensive troubleshooting guide to identify these issues. Vibration is often caused by those repeating forces or looseness we just talked about, but it can also come from resonance or sharp impacts like gear teeth meshing together. One super common trigger is the impact generated by rolling elements repeatedly passing over microscopic flaws in a bearing raceway. And we absolutely can't forget randomly generated turbulence forces. These are a massive headache in rotating equipment dealing with fluids and gases, like industrial fans and blowers. Let's get into the anatomy of these systems, with section 3, the 4 fundamental elements. You know, every single vibrating system on Earth can be boiled down to these 4 physical elements that completely dictate its dynamic response. First, you have mass, or inertia. Second, a restoring element, which provides your springiness. Third, a dissipative element, commonly called a damper, which bleeds off the energy. And fourth, external excitation. Think about a bumpy car ride. The rough road is your external excitation. The vehicle's mass moves up and down. The car's suspension spring compresses and pushes back as a restoring force. And finally, the shock absorber acts as the damper, bleeding off the kinetic energy of the bounce into fluid friction, so you aren't just bouncing down the highway forever. But keep in mind, a spring isn't always a coiled piece of metal. Sometimes we deal with effective spring action. Think of a simple pendulum, or even just a kid's playground swing. There is literally no physical spring there, right? But the mass of the pendulum bob, acted upon by gravity, is constantly trying to pull it back to its resting equilibrium position. So in that case, gravity itself is acting as the restoring springiness. This is where things get really fun. Section 4, physical to mathematical models. Let's talk about how engineers actually translate all this into math. We have to strictly distinguish between physical and mathematical models. And honestly, this transition is where the real engineering problem-solving happens. A physical model represents the actual physical components we want to study.
For instance, we might decide a system has basically zero damping, so our physical model is just pure masses and springs. A mathematical model, on the other hand, takes those physical elements and defines their input-output relations using simplified equations.
To do this, we often start by assuming a very simple linear relationship. We might define a straightforward linear spring deflection, where the constant, let's call it P, equals 1. It's incredibly easy to calculate. But the real world is rarely that perfect, is it? Springs usually exhibit complex, non-linear behavior, hardening or softening as they get pushed further from their resting state. So while we start with simple linear models to get baseline numbers, we eventually have to transition to modeling that complex, non-linear behavior for true accuracy. And damping? Damping is even harder to model accurately. In physical reality, energy dissipates in incredibly messy ways. You have viscous fluid friction inside a shock absorber, Coulombic friction where two dry mating surfaces grind together, and material internal hysteresis, which is actually friction inside the solid material itself as it flexes. If we summarize how we handle this, engineers basically cheat a little bit. We approximate all these complex, diverse types of physical energy loss into a single, simplified mathematical model called linear viscous damping. We do this just so we don't completely fry our computers trying to calculate the messy reality. Section 5. Challenges in modeling mass. Scaling up from simple systems to complex machinery is tough. Let's look at a step-by-step guide on how mass modeling quickly builds in complexity for engineers. First, just figuring out the total mass and inertia of a solid car chassis is hard enough. But step 2, what if that vehicle's a tanker truck? As it drives over road undulations, the thousands of gallons of liquid slosh around. How do you mathematically model a mass that is constantly changing its physical location? And step 3, marine structures. When a ship's hull vibrates, it isn't just the metal ship moving, it actually drags an unpredictable amount of adjacent ocean water along with it. We call this participating water mass, and it severely complicates our mathematical models. As a lead engineer, this is absolutely the kind of thing that keeps me up at night. We are tasked with developing a mathematical model of a vehicle to test its roll, yaw, and pitch dynamics to ensure it's safe. But how on earth do we precisely ascertain the mass moment of inertia or locate the exact center of gravity for an early prototype vehicle that literally does not exist yet? It requires incredibly sophisticated early design estimations and a lot of educated assumptions. Finally, let's wrap up with Section 6, Degrees of Freedom Explained. How do we organize all these equations? A good rule of thumb for engineers is this. A degree of freedom simply refers to the number of coordinates required to completely specify the configuration of a system at any given moment. If you only need one coordinate to know exactly where the mass, spring, and damper are, congratulations, you have a simple single degree of freedom system. Selecting your coordinate system is entirely dictated by how the system's mass can independently move. Let's map this to a real vehicle to see how it scales up. A quarter car model focuses on just one wheel. It has 2 degrees of freedom, the mass of the axle bouncing below the suspension and the car body bouncing above it. A half-car model looks at the front and rear axles together, requiring 4 degrees of freedom, because now we have to calculate pitch as well as bounce. But a full car model, that is a massive multi-degree of freedom system requiring incredibly complex coordinate matrices just to track every single roll, pitch, and yaw of the entire chassis. So we've taken the physical reality of a shaking machine and reduced it all the way down to mathematical masses, springs, dampers, and degrees of freedom. I want to leave you with this provocative thought. When you ride in a car tomorrow, are you just going to feel the physical bumps in the road? Or will you start visualizing the mathematical degrees of freedom and internal hysteresis working continuously beneath you? Thanks for joining me on this explainer. Keep asking those great engineering questions, and I'll see you next time.